In this video, we're going to look at using the technique of integration using partial fractions. So let's say we were trying to integrate this function, 7x plus 17 over x squared plus 4x minus 5 dx. So the first thing that we could try using is substitution. So because the denominator has a larger degree, it has an exponent 2, power 2, and the numerator has a power 1, we would try substituting for the denominator to see if we could use that to get rid of the numerator. So if we let u equal x squared plus 4x minus 5, take the derivative, we get 2x plus 4. So then du equals, just factoring out the 2 from there, 2 times x plus 2 dx. Now, if we compare that to the numerator, the 7x plus 17, there's no way that we're going to be able to turn that 7x plus 17 into this x plus 2 dx. So there's no way that we'll be able to replace this 7x plus 17 dx with this x plus 2 dx because there's nothing that we can factor out of 7 and 17, and there's nothing that we could factor out of the x plus 2 or multiply it by to make it into 7x plus 17. It's just not in the same ratio, those two terms. So substitution wouldn't help us here. We would still be left with the problem of a 7x plus 17 in the numerator and this x plus 2 in the denominator. So in this situation where the substitution won't help us, we need to turn to partial fractions. And the idea behind using partial fractions is that we're going to take this single algebraic fraction, the 7x plus 17 over x squared plus 4x minus 5, that we can't integrate, and break it into an addition of multiple fractions that we can integrate. So we're going to take this single fraction and break it into multiple fractions that are adding together, and then we can integrate each of those fractions. That's the idea behind this. So doing the algebra, this 7x plus 17 over x squared plus 4x minus 5 is the same as 4 over x minus 1 plus 3 over x plus 5. And then each of these terms, the 4 over x minus 1 and the 3 over x plus 5, we could integrate. We can integrate each one of those using this basic rule that if you're integrating a linear term in the denominator, so bx plus a, essentially what we'd be using is substitution. We would end up with 1 over b times the ln of the absolute value of bx plus a, close that off, then plus c. So we could integrate both of these using this property. So if we are able to take this single fraction and make it into these two fractions, we're going to be able to integrate the function. So now the more important question, or the, I guess, burning question, is how do we do that? So how do we go about doing this? Well, first thing that's important to note is that this method is only used when the degree of the numerator, the largest exponent in the numerator, is smaller than the degree of the denominator, the largest power in the denominator. So for the function that we were looking at, the degree of the numerator was 1. It was 7x plus 17, so the x was to the power 1. And in the denominator, we had an x squared. So the degree of the numerator was 1, and the degree of the denominator was 2. So we can use this method of partial fractions. So how do we do it? Well, the first step will be to factor. Factor the numerator, factor the denominator. Then once we've factored, we're going to make individual fractions using each of the denominator factors. So in their denominator, we might end up with one, well, usually more than one factor, but it might be 1 to a power, 2, 3, 4 factors in the denominator, and we're going to make individual fractions from each of those factors using those those factors from the denominator as the denominator of our new fractions. The numerators for those fractions will be unknown constants, a, b, and c, that we're going to be solving for. Then we're going to take those fractions and add them together and set them equal to the original fraction. Next, we'll take those fractions that we just created and combine them into a single fraction. And once we have that single fraction, we'll be able to equate that single fraction to the original fraction, and we'll be able to create equations for each of the variable and a constant or constants. Well, it should be only one constant. So we'll create multiple equations based on that, and then we'll have a system of equations. So we'll solve that system of equations for those unknown constants, the a, b, and c, our numerators. And then once we have the a, b, and c, we'll be able to re-express the integral that we started with as the sum of these new integrals. So using the a, b, and c, putting them into the fractions that we've created, we'll be able to break them apart into those individual fractions that we can then integrate. So let's look at an example of going through this process for the original function that we were looking at. So let's say we want to integrate 7x plus 17 over x squared plus 4x minus 5. So the first thing that we are going to want to do is factor. So we'll look at the 7x plus 17 over x squared plus 4x minus 5. There's nothing that can factor in the numerator, so we'll look at the denominator. The denominator is a trinomial, so we'd be looking for, it's a simple trinomial because the coefficient on the x squared is 1. So we'd be looking for two numbers that add to 4 and multiply to negative 5. So that would be positive 5 and negative 1. So this denominator would factor to x plus 5 times x minus 1. Now we're going to make individual fractions using each of those denominator factors. So we have two factors in the denominator, the x plus 5 and the x minus 1. So we're going to create two fractions, one with the x plus 5 as the denominator and one with the x minus 1 as the denominator. And then we're going to give each of them a constant as a numerator. So for the first one, I'll pick a, the second one, I'll pick b. So now we have two fractions, one for each factor that we had in the denominator, the x plus 5 and the x minus 1. Next, what we're going to do is take these and combine them. So we're going to add the fractions together and set them equal to the original fraction. So we have this a over x plus 5, the b over x minus 1, and we are going to add them together and set them equal to the original fraction, the 7x plus 17 over x squared minus 4x minus 5. Oh, plus 4x. So we have these two fractions that are adding together, and they're equal to the 7x plus 17 over x squared plus 4x minus 5. Now we're going to combine those fractions on the left side. So using algebra to combine those fractions, we need a common denominator for these two fractions, and that common denominator is going to be this x squared plus 4x minus 5, or x plus 5 times x minus 1. So for our first fraction, if we want to have that as a common denominator, we'll need to multiply it by x minus 1 over x minus 1. For the second fraction, to have that common denominator, it already has the x minus 1 in its denominator, so we'll have to multiply it by x plus 5 over x plus 5. And the idea is that this will equal the 7x plus 17 over, I'm going to write that in its factored form, x plus 5 times x minus 1. So we'll have a times x minus 1 plus b times x plus 5 over x plus 5 times x minus 1 equals 7x plus 17 over x plus 5 times x minus 1. And what we can now do is we can multiply the a into this bracket and the b into this bracket. So we'll have a times x minus a plus b times x minus 5b, sorry, plus 5b, all over x plus 5 times x minus 1 equals 7x plus 17 over x plus 5 times x minus 1. So now what we have are two fractions that are equal to each other. The ax minus a plus bx plus 5b over x plus 5 times x minus 1 equals the 7x plus 17 over that same denominator x plus 5 times x minus 1. So now what we can say is if these two fractions are equal to each other, the only way they can be equal to each other is if the numerators are equal to each other. The denominators are already equal to each other, so the only way that these two can be equal is if the ax minus a plus bx plus 5b is equal to the 7x plus 17. So our next step is going to be creating equations from that. So taking this equation with the two fractions equal to each other, the denominators are equal, so again, the numerators have to be equal for these fractions to be equal. So we can say that the ax minus a plus bx plus 5b has to equal the 7x plus 17. And now what we can say is we have these x terms, ax plus bx, those have to equal this 7x. So we can say that the ax plus the bx has to equal the 7x. At the same time, we have this minus a and 5b. Those have to add to the constant term, the 17. So we'd have minus a plus 5b has to equal that 17. So we're making two equations, one for the variable term, the 7x, and one for the constant, the 17. And what we have now are two equations. We can take this ax plus bx equals 7x, and we can say, well, if ax plus bx equals 7x, that's the same as saying that a plus b has to equal 7. So this is going to be one equation, and then our second equation is negative a plus 5b is equal to 17. So now what we have are two equations with two unknowns. So we can now solve these equations to find the a and b, our numerators for our two fractions. So we can solve them using the system of equation solver on the calculator. You could solve them algebraically. I think I'll just do it algebraically here. So we have a plus b equals 7, it's equation 1. Negative a plus 5b equals 17, equation 2. If we just add these two equations together, we'll eliminate the a. So we'll end up with 6b equals 7 plus 17, 24. Divide both sides by 6, and we end up with b equals 4. Then substituting that b equals 4 into either of the equations, I'll go into equation 1. We have a plus 4 equals 7, so that means a is equal to 3. So now we have the numerators for our two fractions. Using the a and b that we just found, we can now rewrite our original fraction in terms of those two fractions. So we had a equals 3 and b equals 4. And our two fractions were a over x plus 5 plus b over x minus 1 is equal to the 7x plus 17 over the x squared plus 4x minus 5. So we can now say that it was 3 over x plus 5 plus 4 over x minus 1 is equal to this fraction 7x plus 17 over x squared plus 4x minus 5, which means that our original integral 7x plus 17 over x squared plus 4x minus 5 dx can be written as the integral of 3 over x plus 5 plus 4 over x minus 1 dx. So we've just taken the original fraction and written it as the sum of two fractions. So the 3 over x plus 5, the 4 over x minus 1. And now we can integrate these two fractions. So we can now integrate this to get our result. So that's going to be our next step. The one thing I do want to say is make sure that the a and the b end up going over the correct denominator. Don't mix them up, keep track of that. So now integrating, we're going to have the integral of 3 over x plus 5 plus the integral of, or plus 4 over x minus 1, which if you wanted to, you could write it as separate integrals. You could write this as the integral of 3 over x plus 5 dx plus the integral of 4 over x minus 1 dx. Importantly, what we're going to use is this rule that if we're integrating a linear expression in the denominator, so bx plus a, and I say it's linear because the exponent on the x is just a 1, then the result is 1 over the b times the ln of that denominator plus c. So the 3 and the 4, those are just constants. So we'd have 3 times the integral of the 1 over x plus 5. The b in this case is just 1. So it's going to be 1 over 1, so don't even have to worry about it. So 3 times the ln of that denominator, x plus 5, plus the 4 in this one is a constant multiplier, so we'll have 4 times the integral of 1 over x minus 1. Again, the b here is just 1, so it's going to be 1 over 1, so just 1. So ln then of x minus 1 plus c. So that means our original integral, 7x plus 17 over x squared plus 4x minus 5 dx is equal to 3 times the ln of x plus 5, absolute value, I should remember to say, plus 4 times the ln of absolute value x minus 1 plus c. And that would be our final answer. So that's an example of using partial fractions to integrate a rational function where the degree of the numerator was larger than the degree of the denominator, and substitution didn't initially help us out.